So in this tutorial, we're going to be looking at carbon storage in oceans. It relates to climate change in the hydrosphere, the atmosphere, and the biosphere. So the first thing I want to point out really is just how important the ocean is in sinking carbon. And the numbers are gigantic. So deep ocean storage is 37,100 gigatons, and the surface ocean 900. So surface ocean alone, it has a greater storage of carbon than atmosphere, and ocean just dwarfs all other sinks of carbon. So it's really important, and any changes to the ocean due to climate change could have a dramatic impact on the ability to sink carbon. So the ocean sinks carbon in two main ways. We've got photosynthesis here through phytoplankton, and this is absorbing carbon dioxide and releasing oxygen. But we've also got carbonate ions in the water that are absorbed and used by organisms to build their shells. So a good example of that is plankton. But also in shallow and deep oceans, we've got coral building, which is a good store of carbon. When these organisms die, they sink to the bottom and carbon stored through sedimentation processes. So it's thought that oceans have absorbed between 30 and 40% of man-made greenhouse gases. And in total, through its ability to absorb both carbon and heat, about 93% of its energy is absorbed by the ocean. And it does this via photosynthesis and sedimentation and shell building organisms. The issue with climate change is that oceans are becoming warmer and more acidic. So as oceans warm, if we start to use this as an example of warming oceans, we can see here that in the photograph, the big problem of coral bleaching. And in the Great Barrier Reef image here, you can see in the north area of the reef, we have 67% dead zones, 26% in the far north. The issue is not as grave in the south and central areas, but this is a significant problem. So corals thrive in ocean temperatures between 23 and 29 degrees Celsius. In these temperatures, the living coral polyps form a symbiotic relationship with different algae, which synthesizes sunlight and carbon dioxide to create nutrients for the reef. And this algae gives the coral its purple and gold colors, the vibrant colors we associate with reefs. When ocean temperatures exceed this critical threshold, this 29 degrees Celsius, they expel the algae, and that can cause these mass bleaching events. If temperatures go back down within that kind of range, they can recover. But it seems that this is now an annual event across most of the world's corals, and it's slowly weakening them and weakening their health and resilience. So this map here shows the extent of the change. We've got clusters of problems here. The red dots show severe bleaching. But what we see in the 2008 image, a 10-year period, we see this huge change. But especially here, if you look at the Barrier Reef here, you've got such a lot of coral bleaching, but around Madagascar and on the east coast of Africa, and right the way across the Caribbean and South America, major problems of coral bleaching taking place. So another problem with oceans and carbon storage relates to the acidification of oceans. So when CO2 is absorbed by seawater, it sets off a chemical reaction. And in short, it increases the concentration of hydrogen ions. And this increases ocean acidity, which causes the carbonate ions to fall in number. Now, it's these carbonate ions that are really important in the building blocks of structures such as seashells and coral skeletons. And so this means that oysters and clams and mussels and corals struggle to build their skeleton shells. And we can see that in the image here of a healthy shell reducing and becoming weaker and frail, and more vulnerable. Now, ocean acidity over the last 200 years has fallen by has increased by 0.1 pH units. And it's a Richter scale, so that means there's been a 30% increase in acidity. So not only is this affecting rates of coral health and contributing to bleaching, but it also affects the calcification rates of hard corals. And it has a negative impact on the rate that corals are able to calcify. Now, this means that coral colonies in the future may become more brittle and less resilient. You can imagine a brittle coral is far more vulnerable to other environmental factors such as storm surges, and these are likely to increase and damage corals in the future. So the extent to which oceans can store carbon in the future is really under doubt. So ocean temperatures have increased globally and have been measured at depths of 1,000 meters. And this really affects all sorts of processes, ocean currents, ocean mixing, depleting oxygen. It disturbs phytoplankton life cycles. So both at the photosynthesis end and in terms of the shell building organisms, we're seeing big disruptions in the way calcium and carbon is stored in our oceans. And a study here by the Limnology and Oceanography letters has shown that in the past 30 years, the amount of carbon that's been removed and stored in deep ocean has decreased by 1.5%, which equates to 100 million metric tons of carbon. That's the equivalent to the UK's annual carbon footprint.